Hello, we are going to work a few problems out of chapter 15. And I think chapter 15 is probably material that's the highest level thinking that you're going to see in an intro chemistry class. You are dealing with just equilibrium, but you're dealing with lots of different circumstances or situations. So having some product added in, doing a titration, making a buffer, just all of these things will make it so you really have to think about what you know about equilibrium. So get your textbook out. We're going to start with problem 1547. So we want to make sure in each case that we read the problem carefully. Okay, so start by reading 1547 with me. So have your textbook out because that's kind of hard to show on the screen and get it big enough. So 47 asks you, which of the following mixtures has the lowest pH? So the first mixture is equal volumes of equal concentrations of a strong acid and a strong base. And so we know that means that we've neutralized all the strong acid and the strong base, and the pH should be 7 because when you've made it all into water, then water autodissociates. And so the pH is essentially dependent on this. Kw for this reaction is 1 times 10 to the minus 14. So when you just have pure water, these are in equal concentrations. So you would calculate that your concentration of each would be 1.0 times 10 to the minus 7. And so when you take the negative log of that, it's 7. We want you to compare that to equal volumes of a strong acid and a weak base. So when we look at that reaction, so we're talking about essentially this right here. So when we put the strong acid in, it completely dissociates. So I make a one-way arrow and I get H3O plus and the base. And so really what I put in is H3O plus to react with the weak base in a neutralization reaction. So we're going to neutralize this acid and make it into water. So what we really need to know to decide if this pH is higher or lower is to see what the K for this reaction is. So this is a neutralization of a weak base with a strong acid. You can look at the beginning of your book. But what you want to do is find reactions that you can add together to get this reaction. So I know I want the base as a reactant. And if I write the base dissociation, where ammonia goes to ammonium and OH minus, that would be a KB. And if I write the reverse of the dissociation of water, so if I need H3O plus on this side, if I put H3O plus and OH minus to form two waters, that reaction would have a K that's 1 over KW. When you add these two green reactions together, you get exactly what we have above. I wrote these in the opposite order, but you get the weak base, the strong acid, forming water, and NH4 plus. So that means that the K for this reaction, which we call Kn, for neutralization is going to be Kb times 1 over Kw. And so I got 1.8 times 10 to the ninth. If I then go ahead and solve, so if I go ahead and solve for this concentration, I start out with 0.1 of this and 0.1 of this. And so some of it reacts forward to make ammonium. So that would be X. And then it'd be 0.1 minus X, 0.1 minus X. So that's 0.1 minus X squared. And so from that, I got a concentration of this guy, Right, I better go through that. Let me grab my calculator. So the X in that case is going to be how much it dissociates. So to find the H3O plus, I have to take the difference. So I should, I know I solved that. Why didn't I write down what I got for X? Well, whatever you get for X, then it's 0.10 minus X equals H3O plus. And you can check and make sure I did that right. Make sure I didn't just say that X was the H3O plus concentration, and then convert that to a pH and see if you get the same value I got here. I don't know why I did this one 2 or 3 days ago, and I can't remember. I should have written it all out clearly. So confirm that this pH goes with 0.1 minus X as the H3O plus, rather than making the error of just using X. And if that is true, then B has the lowest pH. So take a little break and check that. I'll check it and confirm in class. So 51, let's read that one. It says the equilibrium constant for the neutralization of boric acid with caffeine is 24. So boric acid with caffeine gives you the conjugate base of boric acid and the conjugate acid of caffeine, and that has a Kn of 24. And then we want to think about how could we figure out what's the Kb for caffeine. So we want the Kb for caffeine. So if we look at how you could get reactions that you know Ks, you could take boric acid's dissociation in water, so that'd be a Ka. And you can take caffeine's dissociation in water, and that's a base, so that'll be a Kb. But you'll find if you do that, you also need to have the reverse of the dissociation of water in order to get the OH minus and the H3O plus concentrations correct. So if you add these three together, you will, you'll get 2 waters, and the OH minus is the pencil and the H3O plus. So you'll get boric acid plus caffeine goes to exactly what we have up here, the conjugate base and the conjugate acid. So that means that the Kn should be Ka times Kb divided by Kw. And so if I put in the value of Ka and the value of Kw, and I solve for Kb, I got 4.1 times 10 to the minus 4. So this is just basic equilibrium, and remembering that if you can add reactions, the K for the new reaction is equal to the product of the equilibrium constants for the 2 reactions you added. So our next one is 61. So 61 just asks you whether or not the following could make a buffer. And the definition of a buffer is that you've mixed about equal concentrations of a weak acid and its conjugate base. So it has to be a conjugate acid-base pair. They have to be in about equal concentrations so that you have enough of each of those there so they can buffer against both acid and base. So when we look at A, we have HF, nope, this is 61. We have NH3, and we have a strong acid, so HCl is a strong acid. So when you put it into solution, you get an equal concentration of H3O plus. So when these two react with each other, these will pretty much react away and you'll get NH4. So if you look at a Kn, a neutralization for a weak base with a strong acid, it's a very, very big equilibrium constant. So essentially it all goes to NH4. So that means you've used up all the NH3 and you have NH4 plus, but that can't make a buffer because you used up all the NH3. You would have had to have some of that left over. So in the next one, it's the exact same chemistry, except that we start out with twice as much of the NH3. So if we start out with 0.2 molar and 0.1 molar, then you only have enough strong acid to react half of this away. So you'll react all the strong acid, you'll only react half of this, and the half that you do react will go on to form NH4 plus. And so now you do have a acid and its conjugate base in about equal quantities, so that can make a buffer. The next one is a little easier to see. So sometimes you make buffers simply because something is hard to find on the shelf, might not be stable or something. So, and some things are easier to find on the shelf. So in this case, we probably didn't have to make a buffer by reacting some of the ammonia. If in C it says we can add 0.10 molar ammonium and 0.10 molar NH3. And so we have a weak acid and its conjugate base in equal concentrations just by putting it in, not by reacting to create any of it. And so that will make a buffer. Then the next one is similar, except now rather than reacting some base with an acid, we're going to put in the ammonia, and we put it in at twice the concentration of the OH minus. This will be neutralized. So this is a weak acid and a strong base. Has a large Kn value. All of them do if you page back through the first pages of the chapter. So you'll end up with 0.1 here, 0 here. Half of this will react to make NH3. And so yes, you have equal concentrations of a weak acid and its conjugate base. So the next one, I had to pick one out of the text because they just don't have enough of these weak acid, strong base ones. So this is within the reading on page 607. So it's problem 15.16. And it asks us to consider a titration where we have 100 milliliters of a weak acid HOCl, gives us the Ka. Where did I write that down? Gives us the Ka for this weak acid, and it says that we're titrating it with 0.0400 molar sodium hydroxide, which is a strong base. So you have 0.04 molar OH minus. It wants us first to calculate the number of milliliters that are required to reach the equivalence point. So that's before A, B, and C. So we know at the equivalence point, the number of moles of the acid have to equal the number of moles of base you added. So if it's 0.016 molar in HOCl per liter, and I take 0.1 liters, that's got to equal 0.04 moles of sodium hydroxide per liter times the number of liters. And I got 0.04, so that's 40 milliliters will be the volume at the equivalence point. I like to just also calculate the pH before you start, because that just gives you a reference, because you know as you're adding a base, the pH should continue to go up, so it just kind of helps make sure that you know where you're starting from. So before the titration, so I'll call that A prime, before A in the problem, we have just HOCl, and we have 0.016 molar. It's going to dissociate to make the base an H3O plus. So it's going to be x squared over 0.016 minus x equals our Ka. And when I solve for x, I got 2.4 times 10 to the minus 5. X is the H3O plus concentration, so pH equals 4.63. So that would be the first point, the point before we start adding OH minus. And then we move on to A. So A, so at A, we've added 10 milliliters of the sodium hydroxide. So when I add 10 milliliters of sodium hydroxide, if I multiply 0.04, times 0.001, because that would be 10 milliliters, I get 0.0004 moles of sodium hydroxide have been added. I started out with 0.016 molar times 0.1 liters. So I started out with 0.0016 moles of the weak acid. So this you'd call the titration reaction. What happens in the titration? So the weak acid will react with a strong base pretty much to completion, but then we'll have to look at this back equilibrium. So if I say all the OH minus reacts, it can only react away 0.004 moles of the weak acid. So I end up with 0.0012 moles of the acid. I create 0.000, so I create the same number of moles as moles of OH minus that I added of the conjugate base. When I am using a K, I always have to put it into concentration units. So now I have the 100 milliliters plus this is the point A where I've added 10 milliliters. So I have a total volume of 0.1100 liters. And so I got the concentration for the weak acid and the concentration for the conjugate base after the titration. And now we have to think about what happens because those are in equilibrium with each other. So now I have to say, I start with the 0.011 molar weak acid. Some of it dissociates, will give me some H3O plus. But I start with some of this, which I created in the titration reaction. So I start with some of the conjugate base. So I have 0.0036, that should be a 4 there, molar of the conjugate base, and I'm going to create a little bit in the reaction. So if I put that in my equilibrium, it's like the common ion effect. We made some of this in the equilibrium, so we have to take that into account. So Ka equals X times 0.00364 plus X divided by 0.011 minus X. And I got an X of 1 times 10 to the minus 7. And then my pH will be 7.00. Remembering that the number of sig figs that I have to the right of the decimal is always determined by how many sig figs my number has. And the number to the left of the decimal in a pH is considered an exact number. So halfway to the equivalence point, you'll see in a second that this should be easy, but I'll actually go through in detail. So if I'm halfway to the equivalence point, I've added half of 40 milliliters, so I've added 20 milliliters. I started out with 0.0016 moles of the weak acid, and so half of that has been converted to the conjugate base. So I'm left with 0.0008 of each of those, and then I have to start thinking about the equilibrium. So all I did was put the numbers into the titration reaction, where this is exactly half of this, because I'm at half to the equivalence point, which would make this 0.0008 and this 0.0008. So now I just need to convert those to concentration. So take each of these, divide by 0.120, because that's the total liters when I add 20 milliliters to the 100 that was already there. And when I plug it in, what you find is you could have done this much easier, because you end up with 0.0067 plus X times X and 0.0067 minus X. And even fairly strong acids don't dissociate much when you've created a bunch of this base. And so if we do this just with an approximation, we could start out and say X is little relative to 0.0067, which would mean X, because these two would cancel, they'd be 1, and then X would be equal to 3.5 times 10 to the minus 8. So was that a valid assumption? Yes. 3.5 times 10 to the minus 8 would not have altered 0.0067 if you subtracted or added it. So what you find is pH equals pKa at 1/2 to the equivalence point is a pretty good general rule. So X is the Ka, and now it also equals the H3O plus at this particular point, and so the pH went up a little more, up to 7.46. So notice there's a different way to calculate along the way. That's the important part. So at our last point that this problem has us do, we're at the point of equivalence. And so we've added enough OH minus to react all the weak acid away. So when all the weak acid is gone, we have an equal number of moles of the conjugate base. So we just have to take into account dilution. At the equivalence point, it's 40 milliliters. So the total volume at the equivalence point is the 100 that we started with, and then the 40 that we added. So 0.0016 divided by 0.100 gives us the molarity. Someone's going to dissociate. We'll get the conjugate acid in H or OH minus. And this is a base dissociation. So we need to get the Kb, which will be Kw over Ka. And so I got a Kb of 2.9 times 10 to the minus 7. When I solve for X, I got 5.8 times 10 to the minus 5. I did a POH and then converted it to a pH, and I came up with 9.76, which makes sense. Now we've gone to the point, it should be even higher than halfway to the equivalence point, and all we have in solution is a weak base. We've used up all the weak acid, so it should be basic. It should be on the other side of 7. Okay. So 93, let's read that one. We're moving from acid equilibrium to solubility equilibrium. And 93 says, if a saturated aqueous solution of the shock-sensitive compound lead-2-azide has a lead concentration of 8.5 times 10 to the minus 4, what's the value of KSP? So have your book there so you can refer to that. When this compound dissolves, we get twice as much of the azide as of lead. So this is the only thing that dissolved based on how the problem's written. We didn't put any other form of the ions in there. And the lead concentration is 8.5 times 10 to the minus 4 molar. So that means the azide concentration is 2 times that. So it's 1.7 times 10 to the minus 3. And then we can just plug those in, making sure, don't forget to square. So it's this concentration times this concentration squared because of the stoichiometry. So we get 8.5 times 10 to the minus 4 times 1.7 times 10 to the minus 3 squared. And we get a KSP of 2 times 10 to the minus 9. So, yeah, I don't think there's anything else I can say about that one. Read 97. 97 says, use the values of KSP in the table to calculate the solubility of the final compounds in grams per liter. Oops, I did not change them to grams per liter, so we'll have to talk about that. So in A, the compound is silver carbonate, and we get a KSP of 8.4 times 10 to the minus 12. And you get 2 silvers for every one that dissolves, and you get 1 carbonate. So when you look at that, that means the molar solubility is really equal to X. If 1 mole of this dissolved, you get 1 of these. So if I solve for X, so I take 2x squared times X, so it becomes 4x cubed, and I get an X of 1.3 times 10 to the minus 4. That's the molar solubility. How am I going to change that into grams per liter? All you'll have to do is convert, this is how many moles of silver carbonate dissolve. So just use the molar mass to convert that into grams. So take a break and do that. So you know how many moles dissolve per liter, the molar solubility. Convert that into how many grams dissolve in the same volume. So you just have to multiply by the molar mass. So B, come back after you get this. Then look at B, copper bromide. This one's a little easier. KSP will just equal X times X, so X squared. You look up the KSP, you get the X, and then you have the molar solubility. Because each of these you get one of them, one copper bromide dissolves copper 1 bromide. So also convert that to grams per liter with the molar mass of copper bromide. The last one's a little more hairy. We have, this is, copper 2 phosphate. So you'll get 3 coppers for every 2 phosphates. So the KSP is going to be 3x cubed times 2x squared. So that ends up being 108x to the 5th. So when I solve for x, I got 1.7 times 10 to the minus 8, and that's the molar solubility. So take that also to the mass solubility, grams per liter, with the molar mass of the copper 2 phosphate, and just make sure that that makes sense to you. But that's a reminder that anytime you're using an equilibrium constant, whether it's a Ka, KSP, Kn, you're always talking about the concentration units of being molarity. And a lot of times if you're in biology or environmental science, like the drinking water standards are usually given in like parts per million by mass. So you're often going to have to convert these molar units into some other mass unit. Okay, so 1599. Use Le Chatelet's principle to predict whether the solubility of barium fluoride will increase, decrease, or remain the same when you add some of these substances. So the one thing to note is that barium fluoride makes Ba2 plus and fluoride. You can find HF in the weak acid table. So that means that the F minus is the conjugate base of a weak acid, so it's a weak base. So if we add HCl, strong acids react with bases, and if you add HCl, you'll react some of the fluoride away, which means the reaction will shift forward. It will be more soluble. You get more barium 2 plus because Le Chatelet's principle says you take some of this out, has to shift forward to keep the equilibrium expression equal to the same value. In B, we add KF. KF is a soluble form of fluoride. So essentially, we're just adding more fluoride. We know Le Chatelet's principle says if this is at equilibrium, we add more fluoride, it's going to have to precipitate out. So it's going to have to decrease the solubility in order to keep it equal to the KSP. Sodium nitrate is neither acidic nor basic. This is the conjugate from a strong base and the conjugate from a strong acid. So the acidic properties or basic properties of those two are that they're neutral. So neither of those ions is one of the ions that's being dissolved, so there shouldn't be any change. Barium nitrate will be just like B. If you add barium nitrate, you get Ba2 plus NO3 minus. So you're adding more product, so you're going to precipitate it out. So you're going to shift it to the left and decrease the solubility. So the very last one I want to do is 119, and I want to make sure you understand this concept. So in this one that we just did, we talked about the fact that if this is a weak base, if you add an acid, it's going to become more soluble because it's going to react with that weak base. That's really what you're talking about in these ones that talk about the solubility of especially the sulfides in acid. So in general, if we look, let's just look at the table of these that your book will consider important. This is on page A17. They're called solubility products in acid. So they're going to be KSPA values. And when you look at each of those, the solubility can be fairly high, but that's only when they're an acid. Let's see if we can find any of these over here. Probably not. No, it doesn't even give them. Most of the sulfides are so insoluble that unless you put them in acid, you won't dissolve much cobalt or any of these other cadmium, cobalt, copper, Any of those that are in the table on page A17. Keep your book open to that page though, because this problem asks us, are we going to precipitate out cobalt sulfide under different conditions? So the one condition that's the same, or the two, are that we have these quantities of cobalt nitrate and H2S, hydrogen sulfide. We're going to have a different pH in our two problems. But how is this going to happen? So if cobalt sulfide were to dissolve, you get cobalt 2 plus and sulfide, which has 2 minus. But we know, because if you look in the Ka table, there's a value of Ka1 and Ka2 for H2S. That means that it's a weak acid and that it's a diprotic weak acid. So if you think about what that means about sulfide, that means sulfide is a weak base. And if you have acid present, it's going to neutralize that and make HS minus and water. But this is still a weak base because this is a weak acid. So you're going to have that going on to react with another acid to make H2S and more water. So when you add together that whole process, a KSPA is looking at the solubility, so a KSP of cobalt sulfide in the presence of acid. So a KSP in the presence of acid, a KSPA. And so when you add this together, those intermediates cancel, the sulfide cancels, the HS minus cancels, what else cancels? That is all the cancels. And when you add it together, you get cobalt sulfite dissolving in the presence of acid, gives you dissolved cobalt, H2S, and 2 moles of water. So when we think about whether or not the cobalt will dissolve under these conditions, look on page A17 again, right below that table, and notice that they have exactly the reaction I've written, except generically for any M. So our M metal is cobalt, but it's just showing you that this is the reaction that a KSPA goes with. So that means I put this times this over this squared, and that is what has to equal the KSPA. So if we want to decide if cobalt's going to precipitate, we need to see whether or not the ion product is bigger than the KSPA. So KSPA is 3. The concentration of cobalt I'm putting in, because this is soluble, so that's a soluble form. All nitrates are soluble. So if I put in 0.1 molar cobalt nitrate, I'll have 0.1 molar cobalt. Tells me that the H2S is 0.1 molar, and it tells me that the HCl concentration is 0.5 molar. We know that's a strong acid, so that means that the H3O plus concentration is 0.5 molar. So when I put those all in, this is just like a Q, but they call it an ion product instead of a Q. We can see which way the reaction has to go. So this says that the ion product is less than the KSPA. So under those first conditions of a relatively high pH, it's not going to precipitate. The cobalt is very soluble when the concentration of the H3O plus is so high. If we change the conditions, so in the second part, it's the same amount of cobalt and H2S, but we have a buffer and we're keeping the pH at 8. So if the pH is 8, that means that the H3O plus concentration is 1 times 10 to the minus 8, because we just have to change the sign and then raise 10 to each of them. So we'll have 0.1 times 0.1 divided by H3O plus, which is 1 times 10 to the minus 8 squared. And you get 1 times 10 to the 14th, which says yes. If you decrease the pH that far, or increase the pH, which means you're decreasing the H3O plus, that means that these reactions really don't go on and it really decreases. So there will be a precipitate when you've made the pH so basic, because the ion product is going to be greater than the KSPA. So that's a lot of problems looking at applying equilibrium to different systems, acid bases, solubility. There's some on complex formation, which are similar to what I just did. But these problems are challenging. So when you look at them, make sure you think through the whole process and do a lot of writing down what you have,